Hello, we are MIT 808 students, and today we will be taking you through our capstone project titled Application of Deep Learning Techniques in Medium Rainfall Forecasting. Medium range forecasting, which covers predictions from 3 to 10 days ahead, is a vital tool in meteorology as it bridges the gap between short-term weather predictions and long-term climate outlooks. This forecasting range plays a crucial role in enabling early warning systems for severe weather events, which can help save lives and protect infrastructure by allowing authorities and communities time to prepare. In the South African context, early warnings are especially valuable for predicting heavy rainfall. While short-range rainfall forecasts has been extensively studied, medium-range forecasting continues to pose challenges. The aim of this project was to explore deep learning techniques for predicting rainfall and develop a machine learning-based model to predict rainfall 3 to 10 days in advance across Southern Africa.
The dataset used for the study consists of ERA5 reanalysis data spanning from 2009 to 2024. This data is available at a resolution of 1-hour intervals. To make the dataset more manageable, several data processing steps were applied, including altitude filtering, data normalization, feature construction, and temporal and spatial downsampling. After processing, the data was split into training, testing, and validation sets. In the study, two deep learning architectures were explored to model medium-range weather forecasting. The first approach involved developing a custom hybrid model that combines convolutional neural networks with long, short-term memory units. The second approach focused on fine-tuning an existing state-of-the-art graph neural network model known as GraphCast. GraphCast is an open-source deep learning architecture developed by Google for advanced weather prediction. It features a denoiser neural network composed of 3 core components: an encoder, processor, and decoder. Forecasts are generated in an autoregressive manner where the future values are predicted using inputs from previous time steps. This autoregressive design allows GraphCast to maintain consistency and accuracy across multiple days of forecasting. For this study, the model was fine-tuned for the Southern African region to better align with local weather dynamics.
The custom CNN-LSTM architecture developed in the study leverages the strength of both convolutional and recurrent neural network components to model medium-range weather forecasts. Convolutional layers are used to learn and extract spatial features from the input weather data, capturing local and regional patterns across the geographical domain. To model how weather variables evolve over time, long short-term memory layers are incorporated, allowing the network to learn temporal dependencies between successive forecast timesteps. Several modifications to GraphCast were made, including updating the loss function and introducing early stopping. The model weights were incrementally updated through training with the objective of generating accurate forecasts up to 5 days ahead. This process required approximately 18 hours of full training time. In contrast, for the CNN-LSTM model, a tailored loss function was used, and training was carried out with 2 different approaches. This model was trained to produce forecasts up to 10 days ahead and completed full training in about 3 hours, making it more lightweight in terms of computational resources. This slide shows example results for the CNN-LSTM model. The top figure illustrates the predicted rainfall alongside the ground truth for the first forecast day, while the bottom figure shows the third forecast day's results. As seen in the figure, the model performs quite well on day 1, with predictions closely matching the observed data. However, there is a decline in prediction accuracy from the third day, with some regions either overestimated or underestimated in the model's predictions. This slide displays the day 1 and day 3 forecast results from the fine-tuned GraphCast model. GraphCast also demonstrates high accuracy on the first forecast. However, it tends to produce increasingly smooth or average predictions over time. As the forecast horizon extends, the model struggles to capture dynamic spatial shifts in rainfall patterns.
Both models showed improved prediction accuracy during training, as indicated by the steady decrease in mean squared error. The fine-tuned GraphCast model consistently produced more accurate results with a lower root mean square error, as shown in the table. For this reason, the fine-tuned GraphCast model was chosen due to its superior overall performance. This slide depicts an animated recording of the fine-tuned GraphCast prediction shown on the right compared to the actual rainfall observed over a 5-day period in March of 2024. As can be seen, the model generates averaged out predictions of the expected rainfall during the period, showcasing the model's limitation on capturing dynamic shifts in rainfall patterns. Deep learning models demonstrate strong potential for rainfall prediction, particularly in medium-range forecasting, but achieving higher accuracy will require future work, such as integrating high-resolution data for the GraphCast model and adding autoregressive techniques to the CNN-LSTM model.
It is our hope that this study helps lay the groundwork for future research efforts, inspiring more refined models and improved weather prediction capabilities that can ultimately benefit communities. Thank you.